welcome everyone to another edition of the Finite Element Seminar at Livermore. We took a summer break. We're resuming with the talks. Please let us know if you have any suggestions for future speakers. Today is my pleasure to introduce Florian Schäfer. He's an assistant professor at Courant, got his degrees before that from Caltech, from the University of Bonn. And he's a co-director of one of the new PSAP4 centers, the Center for Information Geometric Mechanics and Optimization. And fittingly, he is going to talk about information geometric mechanics.
Okay, well, thank you very much for having me. Thank you all for joining. And yes, I'll talk a bit about our center a little bit at the end, but as Tanya already mentioned, there's maybe no coincidence that I'm talking about information geometric mechanics today. And so this is a research program that is still sort of being defined, but I want to start out by one sort of example of the kind of stuff that we have in mind when we talk about information geometric mechanics. And that is information geometric regularization, which is joint work with my former student, Ruija Tsao. And so the setting or the problem that we're concerned with is shock formation in gas dynamics. And so as in this crowd is probably fairly familiar with, highly energetic gas dynamics tend to develop shock waves, which are on a macroscopic level are jump discontinuities in the pressure, velocity, internal energy of our gas. But then, of course, because of the small but finite viscosity of the gas, as we zoom in, we would see that this like jump discontinuities actually are smooth profiles. Unfortunately, for our numerical purposes, the scale on which these profiles become smooth is much smaller than both the scale of the quantities of interest and also the scale of an affordable numerical mesh, right? So this is on the order of the mean free path, which is in air is on the order of microns. And so in some sense, the simulation of flow with shock is really a multi-scale problem. It's about trying to find macroscopic or grid scale models that can capture the effects of the shock without needing to resolve it. And that is overall the problem that we're going to deal with in the first part of the talk. Now, to make this somewhat more mathematically precise, we're going to give ourselves a simple, like a very simple sort of mathematical model of this equation, which is the barotropic Euler equation, so of this problem, which is a barotropic Euler equation. So, and models a frictionless barotropic gas, where which we can think of if you're not familiar with this equation, it's really a conservation law for momentum and mass. So the idea is that the rate of change, the delta t of the momentum and mass, is given by the derivative of the fluxes. So the difference between how much is flowing in versus how much is flowing out of a given point in space. Okay, and so we can think of these. So as you have maybe noticed, these Euler equations do not have any viscosity, so they don't have a second order spatial derivative in them. And the idea is really that we think of them as modeling the limit of infinitely small viscosity. So of course, every gas has a finite amount of viscosity, but we want to remind ourselves of the fact that this viscosity is so small that we cannot rely on it for numerical purposes. And that's why we take this idealized scenario of vanishing of a zero viscosity, and the solutions that we care about, they're defined as the limit of a small viscosity. So the idea is that we take some finite viscosity, we solve our solution, we solve a PDE, and then we reduce the viscosity, we solve it again, we keep reducing the viscosity and solving the PDE again, and then the solution concept that we have in mind are vanishing viscosity solutions, which are the limit of these solutions as we keep cranking the viscosity to zero. And that's sort of the mathematical idealization that captures gas with the behavior of gas with a very small viscosity. Okay, so now we have a sort of a physical setup and we have some mathematical idealization of it. And so now we want to talk about solving these equations numerically. And of course, in principle, we could always just use a finite amount of viscosity and then some standard finite element, finite volume, or whatever method in this seminar probably maybe more finite element methods, but it's sort of agnostic to the particular method one chooses. But the problem is that if we use a very small viscosity, then from a perspective of a grid, our solution is going to have jump discontinuities on the scale of our grid. And that means that whenever we use higher order methods, so higher order reconstruction of high volume setting or simply higher order finite element methods, we are going to see that they develop these Gibbs-Runge oscillations, right? That just all numerical methods are somehow based on fitting smooth functions. And so if we're fitting smooth functions to something with jumps, we tend to get garbage. And that's also what happens here. And that has been observed a long time ago. And of course, we can say we simply increase the viscosity so that we don't have discontinuities anymore. Well, but then we have the issue that our flow kind of smears out and we're solving a different problem than the physical problem that we set out to solve. And so that is also not satisfactory. Now, in some sense, the oldest approach for dealing with this issue is to use adaptive viscosity. So basically have a viscosity that somehow depends on our flow through some, right here, so the nu depends on our flow variables in such a way that it only turns on near the shock and otherwise goes to zero. So otherwise it doesn't smear out the flow. And the crux of this approach is then to design the so-called shock sensor in such a way that gets as good as possible as distinguishing between shocks and other kind of flow features. Now, there is a huge industry of different such approaches. For reasons that will become clear later, I will focus on one of the most maybe straightforward or vanilla versions of this, which is the so-called artificial diffusivity that takes as the diffusion tensor the negative part of the derivative of u, with alpha being some sort of coefficient that measures the strength of the regularization. And so now, when we apply this to a flow of shock for different alphas, we see that it replaces the shock profile that was a jump discontinuity. It replaces it with a somehow spread out profile. However, we also, so that is good because that gives us more hope to resolve it with numerical methods. But at the same time, we also see potential issues. The first of which is that this profile, even though it is not a discontinuity anymore, it's still somewhat, it has a bit of a kink at the top, if you see, right? So it's not like high order smooth, but it kind of looks like this. And that, if we want to use very high order methods, will again cause oscillations and therefore like Gibbs-Runge oscillations and so on and so forth. At the same time, if we now apply the same equation to an oscillatory signal, so some high frequency sound wave, or you could imagine similar structures arising from turbulence, you're going to see that as we increase this parameter alpha, we're going to over time dissipate this oscillatory structure, because basically the shock sensor always thinks, oh, this might be a shock, and so it adds a bit of viscosity, and that leads to the systematic loss of energy. Whereas, of course, the physical solution for such a high frequency or low amplitude sound wave would be that it approximately conserves energy. Now we can do the sort of a similar thing on the level of the numerics, where we instead use nonlinear numerical method as drop to a low order approximation near the shock. So the effects are somewhat similar, so I don't want to spend too much time on this. I want to briefly mention that, for instance, these methods have some challenges with computing sensitivities of the solution with respect to parameters. And also, of course, there's a certain amount of technical debt that arises from these nonlinear numerical methods, because whenever we do something new, like using neural networks or Gaussian processes to solve PDEs, we have to sort of reinvent a numerical method if the sort of shock capturing is built into the numerical method. And so now there was always another sort of line of work or hope that one could find mechanisms different from viscosity to regularize these equations. And so the first attempt was due to Barth and Fedeco, which was based on so-called Leray regularization, but it resulted in the wrong shock speed. And the second attempt that I'm aware of is based on what's called Saint-Venant regularization or Hamiltonian regularization. but it was restricted to the one-dimensional case, and it also still required some amount of singularities to dissipate energy, which I'm happy to talk more if there are questions about this. But for now, there were two prior approaches that sort of attempted to basically use mechanisms other than viscosity to regularize these equations. And that is where the work I'm going to talk about fits in, which is, to our knowledge, the first inviscid regularization of the multidimensional gas dynamics. And by inviscid, I mean that it's using a mechanism that's different from viscosity, and I'll be explaining more about this mechanism shortly. But before I start, so you see this regularization amounts to having some auxiliary equation that computes this tensor, the scalar field sigma, and then we add the sigma to the pressure. And now if we apply this to the same problem that we saw before, we see now that it replaces these shocks with higher order smooth profiles. And again, the larger alpha, the stronger the regularization, the wider and smoother the profile. But it does so with hardly any additional energy dissipation in the sound waves. So if you see, if we compare again against this localized artificial diffusivity approach, we see that it has generally smooth profiles, high order smooth profiles, with next to no dissipation in these oscillations. So something that's very good about distinguishing shocks with that are replaced with smooth profiles that we can then easily resolve with higher numerical methods without affecting oscillatory structures. Okay, so now, I mean, this equation looks somewhat complicated, and it would have been quite hopeless to try to sort of discover it by just trial and error until it works. But instead, there is a sort of geometric motivation behind this equation that will also teach us a bit about shock formation and different perspectives on it. And that is what I want to present next. So now I'm going to present the geometric origin of this, at first maybe somewhat complicated looking equation. And I'm going to explain this geometric origin first in the case of one space dimension, and in the pressureless case and without external forces. So the pressureless case, that maybe sounds a little artificial, but on the other hand, you can think of it as the infinite Mach number case. So the sound speed goes to 0, and conversely, the flow velocity compared to the sound speed goes to infinity. And for our purposes, this pressureless model is nice because it allows us to define a somewhat closed form solution by defining these phi tx, these paths, so basically, how does this phi tx work? It takes in a point x and maps that point to the position that a particle starting at x has at time t. So that's why it's x plus t times the initial velocity in that point. And then we can write this sort of semi-closed form by what's called the method of characteristic, which simply means that to get the solution at the point phi t of x, we simply trace back the particle that is passing through there right now to the initial condition, and that initial condition then gives us the velocity at that point. Likewise, to determine what the density is in a point, we basically have to understand whether nearby trajectories are rather converging or dispersing around that point. And that is encoded by the spatial derivative of this map phi. Okay, so now we have this kind of concrete closed form solution to work with, and we want to now use this as a perspective to understand shock formation. And the first and maybe most traditional perspective on shock formation is that shocks form when characteristics cross, right? So if you have a particle moving to the right and one moving to the left and they collide, and then to the left you have a positive velocity, to the right you have a negative velocity, and so you have this like singularity in the velocity profile. And we can also view the phi as a whole. So instead of plugging in a particular x, we view the phi as a whole as a function, and then the map t to phi of t, it sort of traces a path in function space. And it turns out that shock formation arises exactly when this map phi ceases to be differentiably invertible. So it ceases to be a diffeomorphism. That, of course, is because when I have two particles collide, then I map 2 points to the same point, and so I cannot smoothly invert this anymore. And so you can now view this as this map phi sort of traveling on some manifold of nice functions, and at some point hitting the boundary of this manifold of nice functions when it just stops being differentiably invertible. We can also view the solution as or the shock formation as arising from forming Dirac measures in our push forward, so in the mass density. And finally, and this is maybe the least conventional way of looking at it, we can look at it through this minimization problem. So here, if you let me briefly unpack this minimization problem, this basically rewards our phi for moving in the direction of the initial velocity, while also sort of regularizing it to not move too far. And now, if you take the derivative with respect to phi of this, so you solve for the optimality condition, you will find exactly that definition of phi t of x equal to x plus t times u0 of x. And so it turns out that we can define that exact same phi through this minimization problem, with again the constraint that particles don't pass through each other, so the derivative of phi is positive. And so it turns out that if you solve this minimization problem for larger and larger t, eventually your particles are going to try to cross, and in other words, this constraint becomes active. And so shock formation amounts to the becoming active of the constraint in this variational formulation. And now we can look at what happens after the shock. So in the first perspective, the gas particles, aka characteristics, merge and sort of like stick to each other and move together. In the second perspective, we hit the boundary of the set of diffeomorphisms, and then we sort of slide along the boundary of the set. From the push-forward perspective, we are propagating Dirac measures. And finally, from the perspective of this, inequality constraint optimization problem, this corresponds to the constraint becoming active, right? So once the unconstrained minimizer would be lying outside of the constraint set, then this constraint becomes active, and correspondingly, again, our solution is going to slide along the boundary of the constraint set. And so to motivate the construction that gives us this regularized equation, I'm going to use this last perspective, the perspective of the constraint becoming active. Because in some sense, if you're familiar with interior point methods in optimization, this kind of structure is maybe not so new, right? So we have this linear objective function plus something that regularizes our optimization variable. That somehow, in this case, forces it to not move too far away from the initial position. And in fact, this looks very much like a homotopy interior point methods, where we would be again having our linear constraint, and then we have some barrier, or more generally a Bregman divergence, that somehow prevents our optimization variable from getting crazy. And in particular, in general, we would use this barrier to prevent our optimization variable from leaving the feasible set. And of course, that's the problem, because in our sort of nominal unregularized problem, this barrier is just the squared norm of phi. And so the squared norm of phi is not doing anything special close to the derivative of phi becoming 0. And so that's why it is not strong enough, if you will, to prevent us from reaching the boundary of the constraint set. And so that motivates us to maybe remind ourselves what we learned from optimization, that in optimization, people use other barrier functions. So for instance, very popular is the so-called log barrier function, right? And the idea is now that we, to this linear optimization problem, instead of adding just this quadratic norm, we're also adding another term that is the negative logarithm of the derivative of phi. And of course, as the derivative of phi goes to 0, this negative logarithm is blowing up, and it's going to become infinitely strong as we move closer to the boundary, in sort of repulsing us and pushing us away from the boundary of the constraint set. And so now if we again form these homotopy paths, so these paths as like we trace the solution as a function of t, we see that before we hit the boundary and slide along it, whereas now we instead asymptotically approach the boundary. Okay. And this asymptotically approaching the boundary, that is really what sort of made this interesting from a regularization perspective, because we can, first of all, we can use this parameter alpha in front of the logarithm. We can use this to decide how brave we are in terms of how close we want to get to the boundary. And then if we express these trajectories approaching the boundary, if we express them in terms of particle trajectories, we see that in this regularized world, instead of colliding and merging, particles only asymptotically approach each other. And this picture here, this picture on the left, that is really key. That gave us hope that this method would be useful, because we see that now these regularized paths, if you zoom out on the left, they are kind of similar to the nominal path. So in some sense, that we are not changing the equation too much. But at the same time, we are guaranteed that these regularized paths never cross. So we never actually form a singularity in this regularized world. And so that means that this way of regularizing the characteristics and therefore the equation that's what made this sort of a very attractive candidate for PDE regularizations. But of course, there's one big issue, which is that it's not clear how to extend this beyond this variational context, right? So in this variational world, I hope what we are planning to do is maybe somewhat clear. But the problem is that the Euler equations are not natively an optimization problem. It's a dynamical system. And so the question is, how do we generalize this idea to a dynamical system? And that is where we're going to introduce a little bit of differential geometry. And so what we are going to just remind ourselves is that the key concept in differential geometry is that we're distinguishing between a point and a direction, right? In linear algebra, we use vectors to both represent positions and displacements between positions. But here we now say in differential geometry, we say we have points or manifolds, and then we have directions in the tangent space of that manifold. And the object that connects these two, the positions and directions, is the so-called exponential map that basically takes in a point and a direction, and it gives you where you end up if you walk into that direction starting at that point for a unit time interval. And of course, the simplest such connection is the simplest such exponential map is the Euclidean exponential map, where you use the sort of vector. You treat just both as vectors that you add, and that gives you your new position. But now it turns out that these barrier functions define another kind of exponential map, another notion of going straight in a direction, which is called the dual exponential map. And this dual exponential map has the following form here, but I'm going to use pictures to unpack this for you. So the idea is that we are in our original coordinate system with our point in our direction, and then we transform both the point and the direction through the map given by the gradient of psi. So now we're in the space that is parameterized by the partial derivatives of psi. And then we do a straight line, like we do a Euclidean exponential map in this sort of like in this gradient space, if you will, the so-called dual space. And then we map back through the inverse of the gradient map. And that gives us our exponential map and our sort of dual notion of a straight line. And now the key observation is that the so-called central path, the solution path on tier point methods, are exactly the dual geodesic generated by the barrier. And so in other words, we can now extend this regularization that before was somehow tied to the notion to this variational form. We can now extend this to general dynamical systems by saying we simply take what used to be the characteristics before, which were sort of going on ordinary Euclidean straight lines, and we now replace them with these strange dual straight lines. Okay, and so now we have sort of a crank that we can turn. So we remind ourselves this is the form of this dual exponential map. So this is the form that our dual straight lines are going to have. We take a time derivative, and so we get a form. We get a sort of first order ODE for this. And then we take a second time derivative, and we get a second order ODE. So this is in some sense an equation of motion. In ordinary, the equation of inertial motion would be phi dot equal to 0. because that corresponds to inertial motion on ordinary straight lines. And now instead we have phi dot equal to some curvature-like quantity that expresses that we're now looking at inertial motion to move on these curved lines. Okay. Now so this is valid for any barrier that we could use, any psi, and now we remind ourselves of psi that was basically the squared norm minus alpha log the positivity constraint. And so basically we just have to now compute all these quantities, the first derivative, second derivative, and third derivative. And so we basically have to take 3 derivatives of this thing, and we do this in function space, so it looks a bit more complicated, but it's really nothing fancy. It's just taking the functional derivatives up to third order. And then we plug this into our what we just derived in our dual equation of inertial motion. And that gives us already the Lagrangian form of our equation, at least in 1D. And so what we have to do now is we have to translate this again back into Eulerian coordinates. And that gives us this modified conservation law. We add back the pressure and the force, and we're done. And that gives us the equation in 1D. Now, what we see is that basically, instead of this curvature term, we now have this sigma here. So you can maybe guess that here you had this sort of elliptic solve that takes some right-hand side, and this basically has become this auxiliary problem that defines sigma. And you should really think of sigma as a, like it's kind of similar to maybe special sort of general relativity, where we think of gravitational force as sort of summarizing or mediating the effects of curvature of space-time, right? That's the discovery channel level of general relativity that I have. And now we can think of the sigma here as acting in the same way, expresses all this geometric complication simply as a pressure-like force that is added to the equation. Now there is some sort of there's some interesting stuff happening when going to the multivariate extension, and that basically comes from the fact that the natural choice, the natural extension would be using the log determinant set of the algorithm, but that is not in general convex, and so we have to use a lifting approach where we lift this to a high dimensional space and then get some basically there's a standard way of inheriting curvature from an ambient space to a submanifold. So I don't want to go through the details here. The main thing I want to emphasize is that, again, also for dealing with this problem, differential geometry gives us a crank we just have to turn. And that, again, gives us a now slightly more hideous-looking Lagrangian equation that has two sort of geometric contributions. But in the end, it's just a crank we turn to translate this into Eulerian form, and that gives us the regularized conservation law. Okay, so this is the geometric origin of where this equation comes from, right? And I want to briefly mention that if you have, let's say, an energy equation or you have other stuff going on, the general rule is just to add the sigma to the pressure wherever it appears. But now I want to take a bit of time to explain to you or try to relate this to something like adaptive viscosity that you might be more familiar with. So what is the mechanism, how, just as a PDE, how this works? So one thing that you can do is you can sort of try to squint a lot and ignore all the gray stuff, the stuff that I've grayed out here. And then you basically see that this is just that this just becomes a Laplace operator, right? Because you have partial xu that is equal to sigma. You plug this in here, and then you get partial xu. So in other words, you get a viscosity-like term. And in fact, again, like this local artificial divisivity approach that I mentioned earlier, in some sense is somewhat reminiscent of this. So if you compare the two, you see that the main difference is that local artificial divisivity does not have this elliptic solve that is applied to the sigma. And instead of the partial xu, it only uses the negative part of the partial xu as a diffusion coefficient. So in some sense, what this means is that if you wanted to interpret IGR, so I think It's not a viscosity, but if you wanted to view it as a viscosity, it would be a viscosity that is both non-local and non-positive, or like sign indefinite. And this has important consequences. So the first thing is that if you now use a really dispersive method like Lax-Vendroff, you're going to see that it's still quite hard to avoid Gibbs oscillations with this local diffusivity, and that's really because the profile is still not to higher order smooth. Whereas IGR is able to get these smooth profiles and then allow avoiding triggering the dispersive error of, in this case, Lax-Vendroff. And the reason is here is really the for this phenomenon is really the non-locality due to the elliptic solve, right? So the elliptic solve leads to non-locality and so information propagation that basically allows you to tell gas particles as they're moving towards the shock to start slowing down before they reach the shock. And that is what allows to get this higher order smoothness, which then helps sort of contain the dispersive error of numerical methods. And now the second, so that is the first difference, the difference in this elliptic problem. The second difference is when we're dealing with this other extreme with the high frequency sound waves, where we see that if we use this local artificial diffusivity, we are going to see observe additional energy dissipation. And basically this happens because every downward slope of this of the signal looks like it could be a shock, and so the local artificial diffusivity adds a little bit of viscosity to it, and so it leads to additional energy dissipation. On the other hand, with IGR, we see essentially no additional energy dissipation. Then again, that's similar to what we observed before. And even if we multiply this tuning parameter alpha now with 100, of course, with this diffusivity, we see that the energy drops like a stone. And still with IGR, we observe next to no additional energy dissipation. And the reason this is possible is because of the sign indefinite of the diffusion tensor, which basically means that for every downward slope, which looks a bit like a shock, the method is adding a bit of viscosity, but for every upward slope, because then this has a reverse sign, it's adding a bit of anti-viscosity. And then this elliptic problem sort of cancels out the viscosity and anti-viscosity and leads to a almost no additional dissipation in these sort of oscillatory structures, even as we crank up the value for alpha. Okay, so now I've explained to you the sort of PDE regularization, and next I want to give you one example of a practical application of this work. So this is joint work with collaborators both at Georgia Tech, especially Spencer Bryngelson's group, and also in industry and at Oak Ridge. And now again, we remind ourselves, okay, I'm sorry, I know this is a finite element seminar, but this happens to be in a finite volume setting. I hope you can forgive that. So that in a finite volume method, the idea would be that we are tracking volumes, then we perform reconstruction sort of on the left for the left and right side of the interface by fitting some higher order polynomial to these averages, and then we compute a flux that goes to the interface, and that's how we update our cell centers. And of course, the problem is that if we now have some like jump, like you see here on the left, then this is going to lead to these Gibbs-Runge oscillations, and so these higher order interpolants are going to become kind of wacky. And a common approach of resolving this is WINO, which basically splits up these reconstruction into sort of lower order stencils, and then only picks the stencils, or preferably picks the stencils that are not affected by the shock, at the cost of introducing additional diffusivity. And so the idea is that now with these sort of regularized shocks that IGR produces, we don't have to worry about this, and we can simply use higher order reconstruction, and we can use higher order reconstruction throughout, and that's it. And here it is important to mention that that this elliptic problem that we are solving here is for practical choice of alpha is going to be well conditioned, and so in practice, just 2 Jacobi iterations of this are enough to solve this elliptic problem. And so now we can add this elliptic this sigma to our equation, and basically replace our limiters like WINO and the corresponding Riemann solver. We can place, we know simply with linear fifth order reconstruction throughout. And so here we see one example of how this performs in the case of so this is basically a 2D Riemann problem, right, where you have the shock wave coming from the upper right, moving towards the bottom left. And I have added this kind of entropy variation. I've added this entropy variation to the initial condition. And so here you see the density, and this initial entropy variation creates these sort of fine scale patterns in the density. And so it's kind of, if you're familiar with this, it's a bit similar to the Shu-Osha problem, just in 2D. And so we now see that for the same resolution, that IGR does a fairly good job at capturing these sort of like fine scale patterns, whereas we know on the same grid scale basically smoothes out these sort of fine scale structures, because as the shock passes through the fine scale structures, we know drops down to a lower order reconstruction, and that washes out the fine scale detail. And even as we increase the resolution, we see that there are some parts of these fine scale structures that we know has trouble capturing after the shock passes through. And to show that this is something that's not just applicable to these sort of small, how you could say, mathematician scale experiments, again, we had this big collaboration with Spencer's group and industry folks, and where we basically integrated this information regularization along the lines that I've just showed into the MFC group maintained by them, MFC code maintained by them, to simulate some backheating problems in rocket engines. And we observed that basically by ripping out all the sort of computation for the Riemann solvers and limiters in the MFC code, we can get a 20 times increase in feasible problem size and 4x speed up for the same problem size. We can get further improvements also by doing a bunch of HPC tricks that I was not myself so much involved with. That's really more like Spencer's group and the industry folks that were leading the charge on this. And in total, this allowed us to conduct the first CFD simulation with more than 1 quadrillion degrees of freedom. And this is also a Golden Bell finalist for this year. Okay, so after having presented the regularization, both from this geometric perspective and from the PDE perspective, and giving you hopefully some idea that this might be something that's useful for real computation and not just for sort of toy problems, I want to go back to the title of the talk and the name of the method, which is information geometric regularization. Because you would have, I mean, I would very well understand if from what you've heard so far, you would maybe think, oh, this might be kind of cute, whatever, but why is this called information geometric? Why is it not just called interior point method or something like that? Or sign indefinite diffusion method? And so let me now make some comments on that are in a moment going to segue us into this, to presenting also our PSUB Center. So, so far we have really been using the dual exponential map as a way of extending ideas from interior point methods to dynamical systems, right? It's just that so far. And it turns out, however, that if we're looking at the probability simplex, so the set of vectors that have positive entries that sum to 1, there's one very special barrier function, which is the negative entropy, which you see here, the negative Shannon entropy. And the dual exponential map associated with this negative Shannon entropy is a very important problem in this field of information geometry, so basically the geometric study of statistical objects, because it's the only way of going straight, the only so-called affine connection that is invariant under information preserving maps, that is geodesically complete, meaning you don't run out of the probability simplex as you follow it, and that is flat, meaning it doesn't have any curvature. And so that means basically it's like the simplest, from a differential geometric perspective, such map that you could find. And so that is why these dual exponential maps are so important as a way of, as if you will, a canonical way of endowing structure on families of probability distributions. And now if you look at our regularizing term, this log determinant of the Jacobian, you see that just by the change of variable formula, this is exactly the Shannon entropy of the mass density. And so now we can remind ourselves that, for instance, if you equip the diffeomorphisms with the L2 geometry, we would be getting the Wasserstein geometry on the densities. So basically, if you look at a L2 geodesic in diffeomorphisms and you look at the push forward of the of a density under them, then this is going to give you a Wasserstein geodesic in the space of densities. And so now you can basically view this as a way in which we take this sort of Wasserstein geometry and we are somehow regularizing it with the geometry induced by the Shannon entropy and therefore by the Kullback-Leibniz divergence. And so this is really I think a much bigger philosophical point, that we can think of this as a combination of the geometry that comes from the physics, right? The Wasserstein geometry, that's sort of or the L2 geometry, that's really the geometry of just like how we expect particles to move on ordinary straight lines. But it combines this with the geometry coming from statistics, which is looking at what would be a likely way of moving around, what would be a statistically very unlikely way of moving around. And so from that perspective, IGR is sort of strikes a balance between the physical geometry and the statistical geometry, which I think is best justified by reminding ourselves that the mass density itself is also some kind of is both a physical, like we think of it as modeling physical reality, but at the same time it's expressing our belief about the physical reality. So it also has this like dual nature of both physical object and the statistical object that summarizes information that we believe to have about the physics. And now, for instance, one can, and that is like a very sort of like ongoing line of research for me, is one can try to tie this deeper into the underlying statistical mechanics, where, for instance, we can recover the Euler equations through making a Maxwellian ansatz for the underlying Boltzmann equation. And then we see that for constant temperature, the log determinant is simply the entropy of this ansatz. And so that really motivates this broader perspective of information geometric mechanics, of saying that normally we view the solutions of continuum mechanics, we view them as basically governing the behavior of representative volumes, right? So it's little kind of fluid parcels or matter particles that basically collide and interact the way ordinary fluids and particles would do. That's sort of how we interpret these solutions if you take physics class or something like that. But in some sense, I think we should rather view them as parameters of probability distributions that summarize some sort of like microscopic statistical physics. And now that they're parameters of probability distributions instead of just represent some sort of matter particles, that maybe tells us something about how we should be evolving them, how we should be discretizing them. And that is really the heart of my perspective on this sort of beginning research agenda of information geometric mechanics. Before I briefly talk about sigma, I want to give you one more example of this approach, which is a very recent work with my PhD student, Brooke, which again follows this idea of if we understand continuum mechanical solutions as parameters of probabilistic models, how should that change how we interact with them? And so maximum likelihood discretization is concerned not with a PDE level regularization, but instead with the discretization of a PDE. And so for starters, we're just going to consider the transport equation, where I'm sure this audience is familiar. We can Galerkin discretize it by making a finite dimensional ansatz for the solution. And basically what happens is that even though we start with, even if our initial condition is a member of that finite dimensional space, as we apply our equation, of course, we're going to leave that subspace, right? And so in some sense, all Galerkin discretizations can be viewed as alternatingly making a very small step and advecting particles and then projecting them back onto our Galerkin space, advecting them again, projecting them back, and so on and so forth. So that's what you see illustrated here. And the standard approach to projection, or to Galerkin projection, is the L2 projection, right? So we would give ourselves these sort of like test functions, and then we say that for all test functions that we integrate with, we're going to have the residual vanish. But we can also view this projection as a statistical problem. So if you imagine, right, you have these particles that are in a certain configuration, then you advect them a bit, and then you try to project them back. So that's really like a statistical problem where you're trying to select out of the Galerkin space, you try to represent the distribution that best represents the data that you get from the advected particles. So the computation of one step of this Galerkin method really is a statistical problem. And if one is doing the L2 projection, then this means in statistical terms that one is using the method of moments. And the method of moments, for instance, has the well-known problem that is dependent on parameterization, and that it can give parameter estimates under which the data has zero probability of occurring, which in the context of these transport equations amounts to a loss of positivity of our solution. And so now from the statistical perspective, we can ask ourselves, okay, so how would a statistician do this? Well, a statistician maybe would not be using the method of moments, but would be using the method of maximum likelihood, which instead of this sort of these like integrating against test functions would try to solve this optimization problem. And in fact, by linearizing around a small time step, we can get a tractable form of this, which is given here, which means that now instead of the L2 projection, we're going to project with a weighted L2 and L2 inner product that is weighted with the inverse of the current density. And the idea is that this inverse of the current density is going to ensure that this projection respects the structure of the probability of the manifold of probability distributions. And so you observe that we get improved relative accuracy. So here you see in red our method and in yellow the DG method, and you see that the DG method tends to produce, even though it's, I mean, up here it's perfectly fine, but it tends to produce large errors in relative accuracy errors, because as you have like some small Gibbs oscillations here, you're going to drop close to zero, and in relative terms it gives you a large error. And for instance, one instance where this is important is if you have a problem where you have large density gradients. So here, if you look at the density, we are plotting a density of a fluid problem now, where the density goes between 2, and this should be something like 10 to the minus 3. And we set the pressure to be constant and the velocity to be constant. So in principle, the solution should just be advected to the right. But what now happens is that if you just use an ordinary DG method for the density, you're going to have these small arrows that push you very close to zero, and then cause the sound speed and velocities to blow up, and therefore the simulation to blow up. Whereas if instead for your projection you use this inner product here, where you weight by the density, you're basically aiming for relative accuracy. And that's why this modified, what we call discontinuous Fischer-Rao-Galerkin, it achieves better absolute accuracy here where the values are smaller, and less absolute accuracy here where the values are bigger. And so it aims for relative accuracy. And that is exactly the right notion of accuracy in order to preserve wave speeds, and therefore, for instance, prevent the simulation from blowing up. So in this talk, I hope I've given you a bunch of a bit of an overview also of maybe my preferred, or like the aspect of information geometric mechanics that I tend to think about a lot these days. I want to again point out that we just recently got this piece of FIC awarded that Brendan, Keith, and I are going to co-lead, and so Brendan has a lot of complementary perspectives on information geometric mechanics, especially for variational problems, more often also for solid mechanics. So there's a lot of synergy, but also distinction there. So I highly recommend you check his work on information geometric mechanics out as well. And we have a really exciting team of experts in solid mechanics, fluid mechanics, control, plasma physics, high performance computing. And so, yeah, we're very excited about this. There's a lot of opportunity for us to send students to the labs, and so that's something that we are all very interested in. And so if anything that I just described sounds like it could be relevant to what you're doing, I'd be very happy to hear from you. And with that, I'm going to ask for questions. Thank you very much.
I have a question. Florian, thanks. That was great. when you add that little term into the equation of motion for the inertial term, and you say you have to do some solve on that. If I was doing that in a fully explicit code, would that cause anything to change with the time steps or anything like that as far as stability?
That's a good question. So far in all experiments, I would say we have, I've never experienced any sort of deterioration of like CFL restrictions due to this. And basically, I mean, the reason why this is maybe not so surprising is because we're always solving for the sigma using like a few iterations of Jacobi, which means that in some sense we're paying up front for it by solving it almost in like an implicit way.
Sure. But is it not a nonlinear equation?
Is it what?
Is it not a nonlinear equation, or is this strictly? I guess this is strictly linear.
Yeah, the equation for sigma. So if you're given this, so the way it works, you're in a certain state, you have a certain u, rho, and maybe e, and for this state, you just solve a linear equation, a linear elliptic problem in sigma to get the new sigma. Yeah. And then you feed the sigma into the, you add it to the p when you compute fluxes.
Okay, so then you basically hold the right-hand side fixed for whatever u you have.
Exactly, and then basically at the next time step, you get a new right-hand side, and you solve for sigma again, and so forth. But the idea is that you always keep the previous sigma as a warm start. So that's the first important ingredient. And the second important thing to note is that the width of the regularized shock is of the order of square root alpha. Right, so here you see for different values of square root alpha, you see that the width of this regularized shock mimics the width of alpha, of square root alpha. And so that means that in order to grid resolve the shock, you want to choose alpha of the order of h squared, where h is your mesh size. And so now when you look at this problem here, you see you have like divergence and grad, so you have you divide by h squared because you have two derivatives here. Mm-hmm. But then you multiply with alpha, which is of the order h squared. And so the system as a whole is uniformly well conditioned as you refine your mesh.
Yeah, I see. Thanks.
Maybe I can follow up on this. I wanted to understand. Can you prove it's actually well conditioned?
Yes.
Independent of rho?
Of rho. So not independent of rho, but if you discretize it the right way and you use a Jacobi preconditioner, you can make it independent of rho.
Okay, so let me follow up on that. You said you can just do two sweeps of Jacobi, but then you're solving this approximately, obviously. Don't all the guarantees that you have here on continuous level go out of the window if that's only approximate?
Well, the good thing is that for these kind of equations, no one has any like guarantees anyways. So there's
okay.
It's like right, like it's a nonlinear multivariate Euler type equation. Like there's no proof.
But in principle, this is a PDE level perturbation. So you do want to solve this. The theory is about solving this exactly, right?
Yes. It turns out that in practice, getting it, I guess maybe one point of it is that we don't, for instance, if you look at these like smooth out profiles, we care about them having the right, like the right, whatever, like height and stuff like that. But exactly how the smooth out profile looks like is not something that is very important for the kind of things we're interested in computing these flows. And so I think that is what saves one. I mean, another way of looking at it is that with any method that does not track shock fronts, I mean, one can at best get first order accuracy in the shock anyways. And so that's why exactly what happens there, so long as it doesn't cause trouble elsewhere, I don't think it's that important.
Okay. Other people having questions, please unmute or put them in chat. Jesse had some good things to say about your work. Very cool work.
Thank you.
Florian. Thank you, Jesse.
And if you introduce viscosity into this, it doesn't hurt anything. Probably just helps. Would that be safe to say?
Yes, I mean the only thing, of course, that you have is that, I mean, if it's physical viscosity, yes, then it only helps. The only thing is that depending on if it is too large, you might need to use some splitting scheme because of CFL conditions.
Sure.
Yeah.
Okay,
so
so
far,
there is a sorry, go ahead.
Yeah, so far we found this to work pretty well. I mean, I played a bit, very preliminarily played around with some MHD equations where one just adds the sigma to the pressure, and it seems to help with the shock capturing. I mean, not the MHD specific shocks, I want to point out, but just like the gas dynamic shocks. Like just adding this to the pressure seems to be a good heuristic before, like as we're understanding more rigorously theoretically if there's some particularly good way of combining this with more fancy equations.
Okay, so Veselin had raised his hand. Veselin, do you have a question?
Yeah, very, very interesting discretization approach. I haven't seen this before. So what happens if the solutions like are close to generating like negative densities? The smoothing that happens here, can it still lead because of the paired approximations of the regularized system? Can you get negative terms there, like negative energies, negative densities? How's that behaving in that context?
Yeah, so the way I view this is that negativity of densities and energies, in some sense, that's not a defect on the equation level, but a defect on the discretization level. And so the way that IGR, the way that this first part of the talk interacts with this is by allowing you to, for instance, decrease the effect of dispersive errors, and then that means less sort of Gibbs oscillations, and so it's you prevent these Gibbs oscillations from pushing your density below zero. That is the way this helps there. And then specifically for that, that's really where this last part of the talk, and we have sort of like, I'm working on follow-up works on this as well to also deal with the energy more specifically, is really that in order to preserve this positivity, what we found very helpful is this modified discretization, which, I mean, again, this is something one can fairly easily integrate in sort of DG methods, where one says instead of using the L2 inner product to project, one use this weighted L2 inner product. And that means that basically your DG method is looking to get the best relative accuracy as opposed to the best absolute accuracy. And that helps with positivity, because loss of positivity in some sense means that you have infinite loss, like infinitely bad relative accuracy.
Okay. Thank you.
Thanks.
Okay, I see a question from Elias. Elias, do you want to unmute and ask your question? Or maybe I can just read it. Can this idea extend to higher order fluid moment equations where each of the full pressure tensor is modeled and solved rather than the scalar pressure that the additional term is added to here?
I would think so. There are a few. So for the first part, for the shock capturing part, my go-to thing would just be to add this to the pressure tensor, like add the sigma to the pressure tensor. And my prediction is that it will help diffuse shock singularities. I mean, that would be my, so that would be the without like making a research problem out of it, the thing I would try and that I would be optimistic that would help. And then I think there's this more general question, which I'm very interested in right now, is whether, for instance, I mentioned here that one can view this regularization term as being related to the entropy of the Maxwellian ansatz to the Boltzmann equation. Now I'm interested also in whether one can, instead of just having it applied to basically only to the entropy, or using only the entropy of the mass density, whether it can use the entropy of the full Maxwellian ansatz. And then, of course, it would be very interesting to see if one can, instead just of using the entropy of the Maxwellian ansatz, one can look at sort of the entropy of the ansatzes for higher order fluids, where I would think that for cases where the pressure is not diagonal anymore, I would assume that that amounts to this ansatz not being isotropic, like Gaussian anymore, but having a covariance matrix. And I mean, these are directions that I'm very interested in, but that becomes more of a research problem. And a similar thing is ongoing work right now with this maximum likelihood discretization, where again, we're using this maximum likelihood approach to project, but in principle, of course, one can again do this in a sort of asymptotic preserving way by incorporating the underlying sort of Boltzmann origins of the Euler equations. And that again, we're working on that for like the Maxwellian ansatz, but of course, it's also very interesting to again see if one can extend this to sort of like higher order approximations of the Boltzmann equation.
Okay, thank you. All right, Andrew, do you have a question?
Yeah. So I had a question about this, I guess, regularization method where or I guess projection method where you divide by rho.
Mm-hmm.
How would you generalize this to say you want to both regularize by rho and say pressure, right, to ensure that both, you have relative errors that don't generate negative densities and pressure? Would you divide the different equations by a different denominator?
Yes, in fact, like the thing that I'm currently working out, you end up having a sort of a coupling in the mass matrix between the energy and density components, which is quite important because, I mean, if you want to preserve positivity of internal energy, basically what you do on the level of the kinetic energy has to be aware of what you do on the level of the total energy, right? Because basically, for instance, the way you easily get negative energies in these equations is if you somehow your momentum transport term transports a bunch of kinetic energy into a cell without you transporting enough total energy into that cell. And then you divide the two from each other and you end up with a negative internal energy. And so that's why this approach that we're working on currently, they suggest a natural way of basically coupling the evolution of these equations. I will say though that at first, I mean, I've been going back and forth because in codes, I usually saw the internal energy, so pressure, become negative first, even before the density becoming negative. But I'm not actually sure that I believe anymore that it's really the problem that the internal energy is, because one thing that's very important about about when your internal energy, when your pressure goes to zero, it doesn't do anything crazy, right? It just means less momentum flux. Whereas if your density goes to zero, it means that your wave speeds blow up. And so I'm starting to wonder how many times when I see negative pressure, it really comes from first the density becoming very small, and then leading to a blow of the equation that then you see in the negative pressure. But actually the first thing that went wrong was the small densities that basically mean that your wave speeds blow up and then your simulation blows up.
Okay, thank you. Any other questions?
Daniel, it's Brandon. I had a quick comment. I mean, I thought this was fantastic, Florian. I'm definitely going to go look this stuff up. Be watching the PSAP too. But so the comment was just that this is reminding me of, I don't work in this stuff directly, but I've seen some stuff in optimal transport, like mesh-free methods for for doing transport equations, and there's similar. This later stuff that you were showing about sort of treating things as probability densities. And I don't know. I don't know if you're aware of that line of work, but similarly, like they're working on different. Yeah. Anyway, there's some. I feel like there's some similarity there. Maybe that's a useful thing for you guys to make some comparisons. I like that this one is PDE based. This is a mesh based and everything. Though that's really nice. And maybe just a quick question. You didn't address this. I'm almost certain that you have this, but so property is that the. Do I take it though that that at least in the limit, that like the entropy generation is correct from this? I mean, all your results look like that's got to be true, but is that like a provable, right? Because shocks do generate entropy. They transfer information, and then you got to, so does it? I mean, guess you were saying like that other method you were compared, you had the wrong shock speed, which would say that it didn't generate the right amount. So do you know that do you have like a proof of that?
So we have, so basically what helps us with the shock speeds a lot is that we are in conservation form. That, so we're conserving the right quantities, and that's, I mean, typically is the key to, basically because of this, there's this something Vendroff theorem, right, that tells you that if you have a conservative approximation, which then basically, if you have an equation that conserves the right quantities, then you can discretize it in a conservative manner, and then that goes a long way in ensuring that you converge to the right solution in terms of shock speeds. So that we observe empirically very robustly, and we haven't really. I mean, I would imagine that maybe one can plug this into this like theorem and then prove something. We haven't gotten around to this. What we have proved so far is in the unidimensional pressureless case. There we can show rigorously that the regularized solutions converges to the entropy solution.
Okay, yeah, that's
basically
a good start.
by means of right. If you remember this pressureless case, we started this with this regularized minimization problem, and we can basically show that this regularized problem, as alpha goes to 0, it gamma converges to the nominal minimization problem, and then that gives us the conversion of minimizers.
Okay, yeah, that's a great start. Okay, thank you.
Thanks.
Okay, thank you. Any other questions? Like, may I ask quickly, does this work for general equations of state? Is there any assumptions on the equation of state, the connection between the pressure and the density and the energy?
So right now, well, you can always add the pressure. You can always add the sigma to the pressure, and I suspect this is going to give you decent results for many cases. I cannot. I mean, in some ways, you can always, of course, like you can. I mean, I'm sure you can cook up some sort of antagonistic, like some very complicated equation of state that basically looks if it.
There's a lot of very complicated equation of states. I mean, there's tables, there are all sorts of things that people do that are highly non-trivial, I would say.
Yeah. So basically, I mean, so I think one way in which you can break this is if you come with equation of states that are very sensitive to the detailed structure of the shock, because of course a smooth out shock is not a physical object. But then again, I would argue that also even a shock that is exactly a jump on a grid scale is not a physical object, because I mean your grid spacing is maybe like this, and the shock is on the scale of microns, right? So that is definitely some of the idea of the of this method is that it is not trying to get you the sharpest shock, but rather it is going to is trying to give you a shock that in its interactions with other waves, like sound waves, behaves as much as possible as a physical shock. And so if you have an equation of state that is somehow very sensitive, whatever, it looks at what the slope is, and if it stays in a certain slope for a certain time, it just explodes or something like that, like you can cook up an equation of state like that, and that would clearly break the method.
Hey, I just want to remind everybody, like you said, John, that Florian's going to be here on Thursday, and so it's going to be out at the L block, and so if anybody wants to come talk some more, they can email myself, and maybe we can arrange a schedule so that people won't be lining up at the door. So yeah, just contact me or Florian, but probably both if you want.
Yeah,
and Bill had some comments in chat about a good test case. Bill, do you want to say more? Newton, say more?
I was just bootstrapping off the comment about equations of state. So there's some non-complex equation of states that have interesting features. You know, certainly a physically admissible rarefaction shock would be a good test on the robustness of the method. You know, you have to be careful. You can also get van der Waals that gives you essentially inadmissible or imaginary sound speeds. That'd be an even tougher test.
Yeah, I will also say that there's we have some ongoing work on sort of trying to. So I still stand by what I said earlier, that for good to first order, basically just adding the sigma to the pressure is probably a good point to start. That might give good results on a lot of problems, but at the same time we have some ongoing work that is basically trying to better integrate this regularization with the equation of state and the pressure. Whereas like so the first thing that we did was just adding them up, and that again gives enough results in many cases, but it's not perfect yet. And so we do hope. I mean, I think in some sense it will come down to a bit of a trade-off between complexity of the regularization and utility. So I'm not necessarily convinced that this more complicated stuff that we're working on right now is going to be the more adopted one, or this simpler, even though maybe not quite as well accounting for the pressure part. So, but we're working on sort of expanding the width of this trade-off available to practitioners.